Good afternoon, all. Welcome to the lecture of Fundamentals in Mathematics. Okay, so in last lecture we have seen what is a system of non-homogeneous linear equations. Okay, so today we will see some examples on that. Actually, a system of linear equation Ax equal to b is said to be non-homogeneous system of linear equations whenever the right hand side matrix, that is matrix B, is not equal to 0. Okay, so let us see its examples. Solve the following system of linear equations. System of linear equations by matrix method. Okay, so first example is 5x plus 7y. 5x plus 7y plus 2 is equal to 0, and 4x plus 6y plus 3 is equal to 0. Okay, now its solution, as we know that the standard system of linear equation is of the form ax plus by equal to c and cx plus dy equal to some uh, e. Then if the right hand side values are not equal to 0, then the corresponding system is nothing but non-homogeneous, so it can be written as 5x plus 7y is equal to minus of 2, and 4x plus 6y is equal to minus 3. As minus 2 minus 3 both are not equal to 0, then the given system of linear equation is a non-homogeneous system of linear equation. Now first we will write this system of linear equation in matrix form. So its matrix form is ax is equal to b. That is, a means the coefficient matrix, that is having it is a 5 7 4 6. X is nothing but x and y, and have value of b are minus 2 and minus 3, where a is nothing but this one will be capital X, and this one is nothing but the capital B. Now as here a is equal to this matrix having entries are 5 7 4 6. Now first we have to see whether it is a non-singular or not. Then determinant of a is equal to 5 7 4 6, and which is equal to 5 into 6 30, minus of 7 into 4 28. 30 minus 28, which is equal to 2, and which is not equal to 0, which implies a is non-singular matrix. As it is non-singular, which implies a inverse exists or is invertible. So a inverse exists, but for a inverse we require, and already we know that how to find out a inverse. A inverse is nothing but the 1 upon determinant of a into adjoint of a, but adjoint of a is nothing but the transpose of the cofactor matrix. So for that we have to find out the cofactor of each element of a given matrix, and then from this one we have to construct a cofactor matrix, and if we take the transpose of that cofactor matrix, then we will get our required adjoint of a. So as a is nothing but, here we will write a having entries are 5 7 4 and 6. Now find out its cofactor. The cofactor elements are now capital A11, which is nothing but minus 1 to the power 2 into its minor, which is 6, which is equal to 6. A12 minus 1 to the power 1 plus 2, which is 3, which is minus 1. Minus of 1 to the power 3 is minus 1 into 4, which is equal to minus of 4. A21 is equal to minus 1 to the power 2 plus 1 3 into its minor, which is 7, and which is equal to minus 6. And A22 is equal to minus 1 to the power 4 into its minor, which is 5, and which is equal to 5. So the cofactor matrix is cofactor matrix is A116 A12 minus of 4 A21 minus of 6, sorry, minus of 7, and A22 is 5. Okay, now just find out its adjoint. So adjoint of a matrix A is nothing but transpose of that matrix. Transpose of this matrix 6 minus 4 minus of 7 5. That is transpose of a matrix, that is cofactor. And now it becomes, so adjoint of A is equal to 6 minus 7, sorry, 6 minus 4 minus of 7 and 5. Okay, so this one is nothing but it's a transpose. Okay, now A inverse is equal to 1 upon determinant of A into adjoint of a matrix capital A, which is equal to determinant of A is 2, adjoint of A 6 minus 7 minus of 4 and 5, just divided by 2. We know that how to multiply by a non-zero scalar to a matrix. We have to multiply each element in a matrix by that scalar, which is nothing but 6 by 2 is 3 minus of 7 upon 2 minus of 4 divided by 2 minus 2 minus 5 divided by 2 as it is. So here we get our A inverse. From A inverse now, as our given system of linear equation is Ax is equal to B, and if we multiply both sides by A inverse, then we get capital X equal to A inverse and into B. And now this capital X is nothing but the unknowns X and Y, which is equal to A inverse is nothing but this one 3 minus 7 divided by 2 minus of 2 5 divided by 2, and what is the matrix B, which is minus 2 and minus 3. Now just multiply these two matrices. Here we get, as this one is a matrix of order 2 by 2, this one is of order 2 by 1, then the corresponding matrix xy, that is coefficient matrix, is of order, sorry, the matrix X of unknowns is of order 2 by 1. It means it contains 2 rows and 1 column. 3 into minus 2 minus of 6, minus 7 into minus 3 plus 21 divided by minus 2 into minus 2 plus 4, 5 into minus 3 minus of 15 divided by 2, and which is of order 2 by 1. Now its entries are minus 6 into 2 minus 12, minus 12 plus 21 9 divided by 2, 4 minus, sorry, 4 into 2 8, 8 minus 15 minus of 7 divided by 2. So this will be the matrix xy. As we know that how to equate two matrices, by the equality of two matrices, x is nothing but 9 by 2 and y is nothing but minus of 7 divided by 2. Okay, so these are the our corresponding values of x and y, and which is the required solution of a given system of linear equations. Now let us cross verify whether this solution, whether these values satisfy the our given system of linear equations. Okay, so here just we have to go to our system of linear equations. What are those? Which are nothing but 5x plus 7y equal to minus 2 and 4x plus 6y equal to minus of 3. Let us check. X is equal to 9 by 2, then 5 into 9 by 2 plus 7 into y is nothing but minus of 7 by 2 plus 2 is equal to 9 into 2 45 divided by 2 minus of 49 divided by 2 and plus 2, which is equal to my 45 minus 49, which is minus of 4 divided by 2 plus 2, which is equal to minus 4 divided by 2 minus of 2 plus 2, and which is equal to 0. So first one will be holds here. Similarly second one also, 4x plus 6y equal to minus of 3, 4 into 9 by 2, which is nothing but 36 divided by 2 plus 6 into minus 7 by divided by minus of 42 divided by 2 and plus 3, which is equal to 36 minus 42, which is nothing but minus of 6 divided by 2 plus 3, minus 6 divided by 2 minus of 3 plus 3, and which is equal to 0. Okay, so both the equations satisfy here for the our given values x equal to 9 by 2 and y equal to minus of 7 by y equal to minus 7 divided by 2. So these are the solutions of our given system of linear equations. Okay, now the second example. If matrix A is equal to 1 minus 2 1, 0 minus 1 1, and 2 0 minus of 3, then find A inverse. Then find A inverse, and using A inverse, solve the following system of linear equation. Solve the following system of linear equations. Following system of linear equations. What are those? They are nothing but x minus 2y plus 1 is equal to 0, minus of y plus z is equal to minus 2, and 2x minus 3y is, sorry, 2x minus of 3z minus of y plus z equal to minus 2, and 2x minus 3z is equal to 10. Okay, so first here we have to find out the A inverse, and by using A inverse we have to find out, we have to solve the given system of linear equations. So as A equal to solution, A is nothing but 1 minus 2 1, 0 minus 1 1, 2 0 minus of 3. Okay, so now first find out its determinant. Determinant of A is equal to 1 into minus 1 into minus 3 3, minus of 0 plus 2 into 0 in minus 2 plus 1 into 0 minus of minus plus 2, and which is equal to 3 into 1 3 plus 2 into minus of 2 minus 4 plus 2, which is equal to 5 minus 4, and which is equal to 1, and which is not equal to 0, which implies A is non-singular. A is non-singular matrix. Non-singular matrix, that is A is invertible, and hence its inverse will be exist. Again, we know that A inverse is nothing but 1 upon determinant of A into adjoint of A, where adjoint of A is nothing but the transpose of the cofactor matrix. So here, just by using the values of A, we have to find out the cofactor of each element. Here 1 minus 2 1, 0 minus 1 1, 2 0, and minus of 3. So these are the, that is, this will be a matrix A. Now we have to find out its cofactor. So the cofactors A11 is equal to, A11 is minus 1 to the power 2 into minus 1 into minus 3 plus 3. A12 is equal to minus 1 to the power 3, which is minus of 1 into its minor, minus of 0 minus 2, which is minus of 2 minus 1 minus 2 minus plus. A13 is equal to minus 1 to the power 4, which is plus 1 into 0 minus of minus plus 2. A21 is equal to minus 1 to the power 3, minus 1 into minus 2 into 3, 6, which is minus of 6. A22 is equal to minus 1 to the power 4, which is plus 1 into 0 minus 2, which is minus 2. A23 is equal to minus 1 to the power 5, which is minus 1 into 0 minus of minus plus 4, which is minus 4. A31 is equal to minus 1 to the power 4, which is plus, into minus of 2 into 1, minus 2, minus of minus plus 1, minus 2 plus 1, minus of 1. A32 is equal to minus 1 to the power 5, which is minus 1 into 1 into 1, 1, which is minus 1, and A33 is equal to minus 1 to the power 6 into minus of 1 into 1, minus 1, in minus of 0. Okay, so its cofactor matrix is this one: 3, 2, 2, minus of 6, minus of 2, minus of 4, minus of 1, minus of 1, minus of 1. Okay, now adjoint of A. Adjoint of A is just a transpose of this matrix. Just take a transpose, it's 3, 2, 2, minus 6, minus 2, minus 4, minus 1, minus 1, minus 1. Okay, so adjoint of A is nothing but this matrix. There will be a small mistake. A2, A22 becomes this one and this one. Minus 3 into 1, minus 3, minus of 2. Minus 3 minus 2, it is nothing but minus of 5. Okay, so this will be minus 5. Sorry, there is a printing mistake. Okay, so this one is nothing but the minus 5. Now from this adjoint of A, we know that A inverse is nothing but 1 upon determinant of A into adjoint of a matrix A. And already we have find out determinant of A, which is 1 into adjoint of a matrix A, which is nothing but 3 minus of 6 minus 1, 2 minus of 5 minus 1, 2 minus of 4 minus of 1. Okay, so what is A inverse? A inverse is nothing but this one. Since 1 upon 1, 1 itself. Okay, so A inverse is nothing but this matrix. Now we know that our given system of linear equation is Ax is equal to B, which implies x is nothing but A inverse into a matrix B. So as x equal to A inverse into B, then just put the values of x, A inverse and B. As here 3 equations and 3 unknowns, then there are 3 variables x, y, z, and which is equal to A inverse. And A inverse is nothing but this one: 3 minus 6 minus 1, minus 6 minus 1, 2 minus of 5 minus 1, 2 minus of 4 minus of 1, and into a matrix B. Matrix B is nothing but 0, minus of 2 and 10. And now multiply these two matrices. Here we get 3 into 0, 0, minus of 6 into minus 2 plus 12, minus 1 into 10, minus of 10. Again 2 into 0, 0, minus 5 into minus 2 plus 10, minus 1 into 10, minus of 10, 2 into 0, 0, minus 4 into minus 2 plus 8, minus 1 into 10, minus of 10. So here this matrix is nothing but 12 minus 10, 2, plus 10 minus 10 get cancelled, 8 minus 10, minus 2. So here x, y, z is equal to this one. Then by equality of two matrices, what is the value of x? X is equal to 2, y is equal to 0, and z is nothing but minus of 2, and which is the required solution. Which is the required solution. Okay, now let us cross verify whether x equal to 2, y equal to 0, and z equal to minus 2 holds our given system of linear equations or not. X is equal to 2, y equal to 0, and z is equal to minus 2. X is equal to 2, y is equal to 0, z is equal to, sorry, here is our z is equal to minus of 2. Plus 2 minus 2 get cancelled, and which is equal to 0. This one will be true. Minus y plus z, 0 plus z, z is minus 2, and which is equal to minus 2. So this one is also true. 2x, 2 into 2, minus of 3 into z, minus of 2. I think there is, yes, and which is equal to 2 into 2, 4, minus 3 to minus 2 plus 6, and which is equal to 10. So this one will be also true. So given values, our given values x, y, z will satisfy our given three equations. Okay, so our required solution will be true. So in this way we can cross verify whether our, that is we have find out the values of x, y, z, whether these are true or not. We have to just put these values in our given system of linear equation, and if satisfies these linear equations, then our required value will be okay. So in this way we can solve a given system of linear equations by matrix method. Now we will take some examples to check whether the given system of linear equations are consistent or inconsistent. How to check? If determinant of a is not equal to 0, then obviously they are consistent since it has a unique solution. But if determinant of a will be equal to 0, then we have to check whether it has a no solution or infinitely many number of solution. So let us see. Using matrix method, using matrix method, examine the following system of linear equations. Linear equations for consistency and inconsistency. For consistency and inconsistency. Okay. So just we have to check whether the given system of linear equations are consistent or inconsistent. Okay. Now, first example, 3x minus 2y equal to 5 and 6x minus of 4y is equal to 9. So let us check solution. The given system of linear equation is 3x minus of 2y equal to 5 and 6x minus of 4y equal to 9. Its matrix form is this one: 3 minus 2, 6 minus of 4 into xy, and which is equal to 5, 9, where a is nothing but, that is ax is equal to b, where a is equal to this one: 3 minus of 2, 6 minus 4. Capital X is a matrix having elements are x, y, and b be a matrix, its elements are 5, 9. Now, determinant of A is equal to 3 minus 2, 6 minus of 4, which is equal to 3 into minus 4, minus of 12. 6 minus of 6 into minus 2, again minus 2. Minus of 12, minus minus plus 12, and which is equal to 0. As determinant of A is equal to 0, which implies A is a singular matrix. A is singular. And if it is a singular, then there are only two possibilities. Either it has a no solution or infinite number of solution. And we know that in last lecture we have seen, to find out how many solution exist for a singular matrix, that is either it has a no solution or infinite number of solution, there is a method, that is we have to find out the adjoint of A into B. If adjoint of A into B is not equal to 0, then the given system of linear equation has no solution, and if it is equal to 0, then it has a infinite number of solution. So here we have to find out the adjoint of A. So as A is equal to the matrix having elements are 3 minus 2 and 6 minus 4. So A11 is nothing but minus 1 to the power 2 into minus 4. A12 is nothing but minus 1 to the power 3, which is minus 1, into 6, which is minus of 6. A21 is equal to minus 1 to the power 3, which is again minus of 1, into minus 2, which is equal to 2. And A22 is equal to minus 1 to the power 4, which is plus, and which is 3. So cofactor matrix is this one: minus of 4, minus of 6, 2, 3. Now, adjoint of A is nothing but adjoint of a matrix A is equal to transpose of this matrix. Transpose of this matrix minus 4, minus 6, 2, 3, and which is equal to minus of 4, minus 6, 2, 3. So this will be our adjoint of a matrix A. Now we have to find out adjoint of A into B. So consider adjoint of a matrix A into a matrix B, and which is equal to adjoint of A minus 4, 2, minus 6, 3, and into matrix B. Matrix B will be 5 and 9. Now check whether it is equal to 0 or not equal to 0. That is equal to null matrix or not. Minus 4 into 5, minus of 20, plus 9 into 2, 18. Minus 6 into 5, minus of 30, plus 27. And which is equal to minus 20 plus 18, minus 2, minus 30 plus 27, minus of 3. And this one is not equal to our null matrix. So adjoint of A into B is not non-null matrix. So adjoint of a matrix into B is not a null matrix. It means the given system of linear equation has no solution. Given system of linear equations has no solution. Okay, so this will be first example. Now let us take the second one. In second example, x plus 2y is equal to 4 and 3x plus 6y is equal to 12. Okay, so solution, it can be written in a matrix form as, can be written in a matrix form as x, sorry, 1, 2, 3, 6, x is nothing but xy, and matrix B is nothing but 4, 12, where A is nothing but this one, 1, 2, 3, 6. Capital X is a matrix having elements xy, and B is a matrix having elements are 4, 12. Okay, so now from this, determinant of A is equal to this one, 1, 2, 3, and 6, and which is equal to 6 minus of 6, which is equal to 0, which implies A is singular. Again we have to use the second method. Either it has a no solution, or it has a infinite number of solution, and for that we have to find out adjoint of A into B. So its cofactor elements are, cofactor elements are A11 is equal to 6, A12 is equal to minus 1 into minus of 1 into 3, which is minus 3, A21 is equal to minus of 2, and A22 is equal to 1. So the cofactor matrix is, cofactor matrix is, what is cofactor matrix? It is simply these elements 6 minus 3 minus of 2 1. So what is adjoint of A then? Adjoint of A is transpose of this cofactor matrix 6 minus 3 minus 2 1. Okay, so now consider adjoint of a matrix A into a matrix B, which is equal to 6 minus 2 minus 3 1 into 4 and 12. Now check whether it is non-zero or 0, that is null or non-null. 6 into 4, 12. Sorry, 6 into 4, 24. Minus 2 into 12, minus of 24. Minus 3 into 4, minus 12. Plus 1 into 12, plus 12. Which is equal to 24 minus 24, 0. Minus 12 plus 12, 0. Which implies adjoint of a matrix A into matrix B is equal to null matrix. And then by the method which implies the given system of linear equations has infinite number of solutions. The given system has infinite number of solutions. Number of solutions. Okay, which is just by our previous method. As if we take as x plus 2y is equal to 4 and 3x plus 6y is equal to 12. So if we take y equal to some k, then from this one x is equal to 4 minus 2k, where k is any integer. Okay, so here for each value of k we will get one solution. As there are infinite number of integers, therefore the given system has infinite number of solution. Since for each value of k we get one solution. Okay, and hence the solution. Okay, so in this way we can check whether the given system is consistent or inconsistent. Okay, thank you for watching the lecture.